In this lecture on fMRI data analysis, we're going to examine some potential pitfalls and other issues. First is a problem called multicollinearity. And in simpler terms, what that means is that two regressors cannot be the same. So for example, if I had this particular time course as illustrated here, and I want to model that with a linear trend, a constant offset, and two regressors that are exactly the same, then really you would not know which of these would be causing this particular response. Mathematically, what's going on is that we're modeling this signal as this beta weight times our regressor of interest plus noise, or in vector format, S is R beta plus this noise. And we estimate this beta using this particular formula here. And this particular matrix is not invertible if there are two vectors that are the same. In addition, the linear combination of any regressors cannot be equal to another regressor. So for example, in this case right here, we have three tasks, task A, task B, and a task C. And if I were to model each of these relative to the others, the sum of all of these is equal to a constant. And that's a problem, particularly if we're going to use, let's say, an analysis program like AFNI, because the constant is by default always included as another regressor. Now, if you look at this more closely, really what we're doing is we're modeling task A versus some baseline, task B versus some baseline, and task C versus some baseline, but there is no condition except for A, B, and C, right? So the solution here is to pick one of these to be the control condition and then model the other tasks relative to this control condition. So we would have essentially task A versus the C, task B versus that control condition. And then fitting these, some of these two regressors, we can obtain the C would be the control condition. What if you have multiple runs? Well, that's really easy. You could just concatenate the runs together and run your analysis. However, there's a few important things to keep in mind. For example, as I've shown here, we ended this particular run right at the end with a particular stimulation. And when we model this response, the stimuli from one run can't affect the signals in the next run that might have been acquired several minutes later. In addition, it's possible that because how the scanner was calibrated at the beginning or so, that each of these runs could have a different mean and perhaps linear trend. So generally, we would have to tell the analysis program to account for these and not allow for the response to bleed into the next run, and also to model the baseline and linear trend separately for each of the runs. Now, in terms of nuisance variables, as I've shown here, we have our ideal response, and let's say we model that with a constant offset, potential linear drifts, and then our regressor of interest. Now, one way we can model this is to include all of these together in one general linear model. We fit that to the data. We call these the nuisance regressors, and this the ideal regressor of interest. We fit these to the data, and we find a nice fit, and we would find that there really is no drift in the data, so the beta weight multiplying this would be close to 0. However, one suggestion might be, well, let's detrend the data first. Let's remove these nuisance regressors. If we do that to this particular time course, you might notice that the linear trend would actually fit somewhat to this data. And if we remove that, we're actually distorting the effective interest. Now, if we were to fit our ideal regressor to this time course, we're not going to get a very good fit. So if we do want to regress all of these nuisance variables out first, what we then also have to do is we have to remove the nuisance from the ideal and then fit that to the data, and then we would get a good fit. Also, some issues related to timing. Note that event-related designs are a lot more sensitive to timing errors. First of all, we ideally wouldn't have any timing errors, but this is particularly important to keep in mind when we're dealing with event-related designs. So for example, here, if I have a block design run, and if I shift the ideal response by 3 seconds, we still have a very high correlation coefficient of 0.9. However, an event-related design would be reduced from a perfect correlation down to 0.5. So just a word of caution to really be careful about the timings and inputting these correctly.